Hello, welcome to this week 6 class of traffic engineering course. So this is a TS session on week 6 content on traffic control at intersections. So it's almost 7 p.m. but no one has joined yet. So I'll wait for a few more minutes and see if anyone joins, and then I'll get started with today's discussion. Hi Vishnu, so I'll wait for 5 more minutes to see if more people join in, and then I'll get started with today's discussion. Yes, so yeah, I'll wait for a few more minutes to see if more people join in. Then I'll get started. Yeah. Okay. Yeah. Yeah. Hello everyone. So I'll start at 7:05. We'll wait for 2 more minutes to see if more people will join. Okay, so it's 7:05 already, so I'll get started with today's content. Welcome everyone to this week 6 TS session on traffic engineering. So today's topic of discussion will be traffic control at intersections. So I'll begin the discussion again with discussing some of the concepts that have been taught in the class, and then we'll move to the similar kind of questions or problems you might find in the assignment. So I'll turn off my video and start sharing my screen. Okay, hope it's visible now. So let's get started with today's discussion. So let me just do this. Okay, so to give you an overview of today's discussion, so the different topics that will be discussed today will include, first of all, is intersections. So these are basic concepts. I think there were no maths involved in this. So intersection and conflict points. So it's just knowing these things, understanding these things, and so on. Then there were different levels of intersection control that were discussed. So I'll talk about all this in this session. Then again, there were warrants for traffic signal control. Then next topic is on operational characteristics, so signals and operational characteristics. Next is, I think, there were discussion on flow at signalized intersections. And I think there were another discussion on delay as a performance measure. So these are the topics of interest in this session. And let's get started with some of the concepts of the first topic, which is intersection and conflict points. So let me, okay, I think someone has joined. Okay, so let's start with this topic, um, intersection and conflict points. Now here, first, I think there were basic examples that were given where two or more roads kind of meet, like converge or diverge. So that is called as an intersection. And there are certain major accident spots that you can identify because of those. And that's how it's kind of related to conflicts as such. And the key considerations in intersection design, let me write those. So key considerations, intersection design. These are uh, satisfying traffic flow needs with available capacity. And one more thing is enhancing the safety. And because you need to enhance safety, you have to identify the conflict points. So conflict points, if I have to define it, they are uh, locations where traffic movements merge, diverge, okay, yeah, and or cross. So now there were different examples of this were given of this conflict points. So let's see some of these. So let me say this. Okay, so we had this figure in the slides. So, so here you can see that first one, it's showing the crossing of two, say, major roads. So one is marked in blue, another is in green. Then there are this crossing that happens. So there is this through moving traffic, and there is some crossing that happens. And the crossing can be in this kind of a nature as well. Weaving happens as well. And these are examples of diverging and merging. And this is a like a classic example of where there is no conflict. So these are the potential spots where accidents might occur, and that's why you have to enhance safety, and you have to identify this first. And based on that, you have to come up with certain safety measures that we'll talk about later. So the next thing that were discussed was two different kinds of intersection, and there were how many conflict points. So the complexity of this was shown. So let me open another slide. So it's on intersection and conflict points again. And let me just do this and insert an image. So these images, these two typical examples were given in the class. So where you have a four-legged intersection, or you can call it a single approach four-legged intersection, and another is a three-legged intersection. And it's nicely shown in the figure where the crossing happens and where the crossing or the turning happens and the merging and diverging happens. And using this, you can find out exactly how many conflict points you have for both these types of intersections. So, as I have already mentioned, that intersection crashes are related to the number of conflicts that are present in the intersection. Now, if I have to write it down, the number of conflict points here in this scenario, so let me do that. So let me insert a text box. So for the first case, it's for single approach four-legged intersection. So here what you have is, let me increase the font. So you may be asked to determine the number of conflict points. So there are three different kinds of those. So one is crossing plus turning. Then another could be merging, and the other could be diverging. So these numbers you can easily find out using this figures, and since these are already marked here, so the crossing that you can see here, it's that there are 4 points where this crossing happens. And then there are other crossings that you can also call it as turning. Those are these green points that are in between. So these are three for this four direction actually. So 3 times 4, those are 12. So this is 4 plus 12. So this is kind of happens in this portion that you can see. And these are in total 16 numbers. So this is 4 plus 12 equals 16. Then for merging, you have uh, this blue markers that are shown here. So here, I think you can notice that there is this merging happening here. So these are marked as blue. Another merging happens from here. This is marked as blue again. So again, diverging is also marked as blue here. So this is an example of diverging. So this is an example of diverging points as well. And if you work it out exactly, so you will find out there are exactly 8 merging and 8 diverging points. So the total number of conflict points is 32 in this situation. Whereas if you look at the other figure, which is a three-legged intersection, you can notice that the number of conflicts points is significantly less than what you have in the other scenario. So here, I think you don't even have a crossing conflict type. For the turning, you have, I think, around three. Yeah, it's these three that are present. And then you have this merging and diverging. So I think you will have, this is a merging one. Okay. Then I think this is another merging. And here I think there's another merging. So you'll find three merging and exactly I think three diverging that will happen. So similarly, you can write it's going away. Just reduce this. So for three-legged intersection, you have crossing plus turning equals 0 plus 3. Then you have merging equals 3 and diverging equals 3. So the total conflict points here is 9. So you can draw this kind of a conflict diagrams and come up with these numbers, and that will give you how like probable it is to have crashes at those intersections. And then we'll move on to the measures and we'll talk about it later. So now there were discussions on, I think, factors that affect a driver's ability to avoid conflicts. So for which I think there is a simple illustration that would be helpful to understand. So let me just copy this. So here there was this figure which shows you that so this vehicle is wants to move to this lane in this intersection, but this vehicle is also coming from the opposite direction, and this vehicle is also moving in that direction as well. So typically, if you have this kind of a buffer zone like 4 seconds or 6 seconds gap here, so you can do this movement without any issues. But if this is not the case, if the uh, density is high and the headway is less, then you might have to have some measures to control traffic and so on. So, presence of reasonable opportunities for this safe maneuvering at the existing volume levels that should be there. So, if it is there, then driver is able to avoid conflicts. Now, intersection design typically aims to minimize the number of this or the severity of potential conflicts. So let me write it down. So let's insert the text. So the key points that you have to remember here is that so this is typically done to minimize the number and the severity of potential conflicts. And this can happen between different vehicles as well as pedestrians. So it can be cars, buses, I think trucks, right? Then you can ride pedestrians and so on, right? So that's the aim that you have for to do this intersection design. And there are different ways of doing it. So different approaches include, one is say priority control, the other is space segregation. So I'll talk about it detail later. And then there is time segregation. Okay, so that's the basic concepts of this intersection and conflict points. I think the next discussion is on levels of intersection control. So let's move on to that discussion. So here I'll be talking about levels of intersection control. Okay, so we have three levels of intersection controls, and these are classified as level 1, which is named as also passive control. Then you have level 2, which is semi-control. And finally, you have level 3, which is active control. Okay, so here in passive control, these are typically basic rules on the road, and this includes, say, signs or road markings and so on. In semi-control, you have a direct assignment of right of way using yield and stop signs. So these are yield or stop signs. Then you can have channelization as well. And finally, for active control, there are two different things. One is signals, and the other is grade separation. Okay, so these are the basic thing. Now you have to know how this passive control and the other things, semi and active control works, and exactly the operational characteristics of these things you have to know. So now this intersection control again depends on driver's ability to perceive or avoid this different, say, type or level of conflicts by their own judgment. And if the capacity of the intersection is adequate, then with desired level of service. So that is another thing that kind of depends whether the intersection control is required or not, and so on. So for passive control, so let's have a brief discussion on that. In passive control, what you have is here, this is applicable where right of way is not explicitly assigned through the use of signals or signs. So driver is expected here to obey the traffic rules of the road, such as say right of way rules and so on. And the driver of vehicle approaching an intersection must yield the right of way to any vehicle or pedestrian already in the intersection. So these you have to follow, and when two vehicles from different roads are approaching an intersection at around the same time, driver on the left must yield the right of way to the vehicle on the right. So here there can be measures, so it's not related to say stop signs or yield signs, but still you have to put some traffic signs and road markings. So as I mentioned before as well, so this let me check it. So, so this passive control, so this includes, say, this, you need to have this traffic signs for this, road markings, and sufficient sight distance is essential for safe operation. And in this context, I think there was a discussion on sight triangle at an intersection. So maybe let's briefly talk about that one. So sight triangle. So here what you have, let me add an image quickly. So you have this kind of a scenario where vehicles are coming from this road and this road as well to an intersection. And these are the distances, so-called. So from this point to this intersection, which is D2, and this is again D1. This vehicle is moving with, say, with certain, so the volumes I think are given in different roads here. Uh, Mm, But no, sorry, these V's are here denotes the design speed of those roads. So V1 and V2 denotes the design speed of this too. So here, what you have, you need to have clear visibility so that there is no chances of collision at that intersection. So drivers should be able to see each other in a sufficient time or distance to be able to halt their vehicle. And as I have mentioned about halting their vehicle, so this is related to the stopping or the safe stopping sight distance. I think that you already might be knowing the formula. It's, I think, Vt by Vt plus V square divided by, I think, F plus minus some 0.01 G, and then you have to do some unit conversions as well for that. So here you have to ensure that whatever the safe stopping side distance that you are getting, suppose this ds. So let me maybe write down those three scenarios that were discussed in the class. So, insert text. Okay, so here, so ds is the safe stopping distance, as I have mentioned. Now, I think this in the situation where I think this should be given small d1, yeah, d1 equals, say, ds, then if you have d2 greater than or equals ds, so this will imply the intersection is safely operated under the basic rules of. Now, if you have another situation where this d2 becomes less than equals or strictly less than ds, then you have to have some sort of control measures. So implement control using stop or yield signs or signal. Then also you have to do some lower the speed limit on the major street to a point where the sight distance is adequate, or remove or reduce the sight obstruction to provide adequate sight distance. I think it was discussed in the class that though this sight triangle should be like clearly visible without any obstruction, I think in the Indian context, you don't typically have those kind of scenarios in many places, because you might be having a shop and so on, or there could be some other structures that could be present there. So typically for safe movements, you have to have this kind of a scenario, and these conditions has to be satisfied. So maybe I'll just quickly write down the remaining key points here. It's the lower the speed limit on the major road, major street, or there could be remove the site obstruction. Okay, so I think this was the preliminary discussion on this topic, intersection and conflict points. And after that, I think in the next uh, module, or yeah, it was E2, I think. So this is basically till now it's very simple discussion on passive control. But you have talked about briefly about signals and so on, but that comes later. Before that, we can have a brief discussion on semi-control. So let me write this down. So let's discuss more on this levels of intersection control before I move to the problems that we'll find in the assignment. So here, what you have is, let's talk about the level 2, it's the semi-control. And as you'll be knowing that this includes that stop or yield signs that I have discussed. So let's quickly maybe have a picture. So these are the typical kind of settings that you have for this level 2 intersection control. And here the major or the minor roads where this is applicable, where the right of way rule would not be expected to provide reasonable solution to your situation, and the minor street entering a designated through highway or unsignalized intersection with a signalized area and so on. So that could be the settings here. Okay, so next, so this is about this. I think this is stop sign example to begin with, where the vehicle has to be stopped completely. Then there can be another, it's the each side application, where this vehicle controlled by each side need to slow down to a reasonable speed. So basic differences of those two. Uh, Maybe I'll just add a text. So let's talk about the first one, which is the yield sign. So vehicles need to slow down to a reasonable speed. And then this is not always, a stop is not always required, like a full stop or something. So there can be an example where, say, for a channelized turn lane that is separated from the adjacent travel lanes by an island. Then, if you look at the stop sign, so Mm. A complete stop is required, as the name suggests, and if a stop is always required on minor streets because of one or more of the following like conditions that were there in the slides. So I think the condition included the depending on the vehicular traffic volumes on the through street. Then there were other factors such as restricted view, and then crash records, like past or the crash history records, whatever we call it, crash records. So based on that, you have some criteria whether to put a stop sign or not. Like if you have more than, I think, 3 crashes in a year or more than 5 crashes in a 2 year span, then you have to put a stop sign at that intersection. Okay, so next discussion was, I think, on channelization using this concept of level 2. This is semi-control measure. So maybe I'll just add one more figure. Okay, so these represent the channelization. So I'll be talking about more of it if there are similar questions in the assignment. But here, maybe just have a brief concept where this is done, where the separation of conflicting traffic movements into definite paths of travel by traffic islands or pavement marking. So this is an example of a roundabout, and this is a channelized intersection with a central island around which traffic must like travel clockwise, and entering traffic must yield to circulating traffic and so on. So that's a kind of a high level view of this semi-control. Next is the level 3, which is the active control. So we can have a brief discussion on that. Then we'll move to the other topic. So, so the third one is level 3, is the active control. Okay, so here this is applicable for high intersection volumes, restricted site distances, and uh, related crashes, those history that I have mentioned. So for which you need is traffic signalization, and this can be done using, this is a time segregated right of ways assigned to the various traffic movements, so that will reduce the conflicts. And like traffic control signals are devices usually installed at the great intersections and built up areas. So these are the basic concepts, and it can enhance your safety and increase capacities and orderly movements of traffic, reducing the crashes and so on. But there are certain disadvantages with that as well. So let's write down both. Advantages could be improved safety. Then you have increased capacity. Then orderly movement traffic, and then reduction of severe crashes and so on. But on the other hand, if you have to ensure all those things, you will end up with some disadvantages, and that will include increased delay, then increased use of less adequate routes to avoid traffic control signals, some collisions, potential increase in the frequency of rear-end collisions and so on, but delay is the main thing here. Then I think there was brief discussion that we can have on grade separation, which also falls under this active control. And if this is kind of you go for it when signals cannot like have a significant benefit in reducing this conflict point as such. So then this will give you a greater efficiency, safety, and capacity. So this is greater safety, efficiency, and capacity. So there could be highway grade separations without ramps and interchanges. Those kind of examples are there for grade separation. Now, there are different warrants for interchanges. So highway full control of access in sufficient capacity at the intersection, disproportionate frequency of serious crashes, long delays, and so on. So in this context, I think these warrants and so on were discussed, I think, somewhat later. But before that, I think there were a brief discussion on data requirements for justifying traffic control signals. And I think there were different kinds of data that were discussed. One is, I think, a period of 12 hours that was considered. So maybe just discuss those data requirements. So here, the number of vehicles entering in the intersection in each hour from each approach during 12 hours of an average day. So that's one thing, 12 hours of an average day. And there are some metrics on volumes and so on. As I mentioned, vehicular volumes for each traffic movement classified by vehicle types during peak hours. So there can be another which is peak hours. Then there can be pedestrian volume counts. Then delay data, stop time, delay data, and queuing information and so on. There can be other uh, data requirements like information about nearby facilities or the statutory speed limit or the 85th percentile speed. So speed limits. Then you have something called condition diagram, which tells you the physical and geometric features of the intersection. And another is the conflict, or sorry, the collision diagram. So that gives you some estimates of crashes and so on by different types, location, direction of movements, and so on. So these are the data requirements. After that, there were discussion on this warrants for traffic signal control. So I'll get into that discussion, but before that, maybe so there are 9 warrants. So let's list it down first, and then I'll move on to the other ones. So this is called as the MUTCD warrants for traffic signal control. So there are nine warrants, and this is called as the Manual on Uniform Traffic Control Devices. So you have warrant 1, which is 8-hour vehicular volume. Then you have warrant 2, which is 4-hour vehicular volume. I am not listing down everything, just maybe the first three. Others you will find in the slides. Then you have warrant 3, which is the peak hour volume. And then you have different pedestrian volumes, school crossing, coordinated signal systems, crash experience, roadway network, intersection near a grade crossing. So total 9 warrants are there. And then satisfying one or more of the warrants should not in itself require installation of a signal. So that's why a comprehensive engineering study is conducted, and a traffic control signal should not be installed unless this engineering study indicates that installing a signal will improve the overall safety and the operation of the intersection. So that's the gist of this thing. Maybe I'll discuss more of it later. So I'm not sure how much of it was discussed. Okay, I think different warrants were discussed in detail after this. So I will get into that discussion. So also with respect to I think IRC 93 as well. So and after that I think there were full discussion on signaling and so on. So let me maybe go to the assignment questions that are relevant to this, and then I'll switch to this discussions if I have time after that. So let me open the assignments. Okay, so the thing that could be relevant here. Okay, so let's start. So state true or false. Sufficient sight distance is not essential for safe operation under level 1 control. So at intersection, then you have traffic sign, sorry, traffic signal. It's an example of level 2 signal, level 2 control. 3 is driver is expected to obey the basic rules of the road, such as right of way rule under level 1 control intersection. Okay, so what would be the answers to this? Yeah, nobody will reply anything. Okay, so the first one says that sufficient site distance is not essential for safe operation. Okay, I think there is some reply. One is false, that's correct, because it is essential, and we have seen it in terms of that side triangle as well. Second one is also false because it is a level 3 control. What about the third one? This one reply, yeah, true, that's correct. So that's basic thing that went. I think this was discussed earlier during the discussion on level 1 control. So this was a simple problem. Then next is there is something about this MUTCD warrants, and there is a question on matching. So let me solve those. Okay, so you have so it's a matching problem. First you have warrant 2. This side you have volume of intersecting traffic. So here you have warrant 3. You have copper platooning of vehicles. Okay, next is you have, sorry, so this will be warrant 3, sorry, warrant 6. This will be due delay on minor street traffic. And finally, the fourth one, which is warrant 7. So this is say severity and frequency of crashes. So you have to do this matching. So what would be the answer? Can anyone tell me? So it will be, I think, be discussed in that lectures. I just gave you a brief introduction to those MUTCD manuals, sorry, the warrants. So, but I think you'll be able to answer it. So let's see what warrant 2 means. So what would be warrant 2's answer? So warrant 2, I think, dealt with that 4-hour vehicular volume, and during the discussions, I think it was mentioned that for each of any 4 hours of an average day, so this is typically taken, and there is that 85th percentile speed on major street if that exceeds a certain speed limit, or the intersection lies within a built-up area of an isolated community. So those also affects this warrants that you have. And the principal reason here was mentioned about was on volume of intersecting traf traffic. So that's the correct answer here. So warrant 2 is 1. 1 is A here, so that's fine. Next is you have warrant 3. So that gives you, so warrant 3 is on peak hour thing, and there were reasons that are mentioned. So anyone has an answer to this? So warranty is kind of applicable to office or industrial complexes, high occupancy facilities, and so on. And this is taken for any like 4 consecutive 15 minutes period where all the conditions are kind of met. And then you look for total stop time delay, minus street volumes, total intersection volumes, and so on. So as I've already given you the word delay, so this is the reason why this happens, and this is due to like undue delay on minor street traffic. So that's the correct answer here. 2 is C. And okay, then you have 3. So here the correct answer would be, so warrant 6 is for, I think, coordinated signal system. And again, the reason is progressive movement in a coordinated signal system. Like sometimes that necessitates installing traffic controls at intersections to maintain some proper platooning of vehicles. So that is the correct answer in this case. So you'll find more discussions on it in the lectures. And finally, the warrant 7, that will give you the severity and frequency of crashes, and all the like some criterias were given, so those has to be met, and accordingly you have to see this warrants can be applicable or not. So this is the main kind of discussion on this. So the answer to 4 will be D here. Okay, so did anyone mention it? ACBT again. Okay, someone said please open assignment. Okay, yeah, but why do we need to open assignment? I am writing the questions. That's fine, right? Or if you have any doubts, you can ask me later. Okay, ACBD is the correct answer. Yeah. Next, let's see what are the questions that are given. Okay, so there is another on, I think, true false type. Okay, so the first one is full stop is always required to the approaches with yield signs. Next is uh, yield sign provided along a minus grid approach entering a designated through highway. Next is e-signs can be provided for unsignalized intersection with a signalized area. And I think there is another one, e-sign are used at intersection with a minor and major road where application of right of way rule would not suffice. Okay, so let me see if there is another. Okay. 200% option A. What is 200%? Okay, I didn't get you. Okay, nice. Why do you say it as 200%? It's 100% is enough, right? Okay, next is this is true. Uh, then this is also true. And finally, this is also true. Okay, so I think that was pretty much it about this. Maybe let's take a problem now. I'll come back to the discussion of more of the content later if I have time. Because we are having only around an hour left, and let's see if we can solve some problems related to, I think, signaling and so on. So let's do this. What I'll do, I will include a figure. So the problem would be, yeah. So the problem says so, so this is the total critical lane volume in vehicles per hour based on the above figure. So that you have to find out. So what would be the approach to solve such problems? Can anyone tell me? Okay, so we have this A1, A2, A3, and You also have this volumes that are written based on this different conditions. So you have to find out the critical lane volume. So I think the discussion of critical lane volume comes in module point 3 or point 4, around somewhere there, I guess. Yeah. So you have this phase diagrams that is given here, and from which you have to find out. I think there was an example in one of the slides as well. So that was, I think, more of a basic example with A1, B, and C. Now you have A1, A2, A3, B, and C. So typically what you have to do, you have to add up some numbers, and those numbers should be, you have to look at this figure and determine what those numbers are. Okay, if anyone replied anything. Okay. Oh, the previous one, someone said 1 is true, 2 is true, 3 is true. That is not the case. In the previous one, 1 is false actually. It was not true. Because that's the basic definition of yield signs, right? You need not stop completely. You can just slow down. That's all. Okay, for this problem, someone said, okay, 1240 is the answer. Okay, let me check if that's correct or not. So for the first one, so consider this A1, A2, and A3 combined. So if you have this, so it's kind of, first you have to take the max of 140 plus 450, comma 250 plus 420. So what I'm doing, I'm just adding this two up, as well as I'm adding this two up. And the one that gives me the greater value, that should be the contribution of this critical lane volume from this portion. Then you have, for the other one, it's very simple. It's just the max between these two. So it's max 200, 220, plus you have now 350 as well as 280. So you have to, it's again very simple. So it should be max of 350, comma 280. So this gives you, the first one is 590, I think, plus, sorry, comma 670. So that's 670 plus 220, and then you have plus 350. So this gives you a final answer of, I think, 1240 vehicles per hour. Okay, so I think the answer is correct. Yeah, what you said. That's, yeah, it was an easy problem, not that difficult. I hope everyone has understood this. Okay, so now let me, I think, take another problem or another set of problems. So I'll give you this data, and then you have to find out the individual this problems that I'll be giving. So this is on, the next one is on signal designing and so on. So the data includes, so this is an approach at a signalized intersection with the uh, following known characteristics. So first one is, maybe I just list it down, it would be better. 85th percentile approach speed. So this is 60 km per hour. Then you have grade plus 3%. Then you have width of intersection. This is stop line to far side, no conflict point. So this is 30 meter. Next you have average length of vehicles. So this is 5 meters. Next you have deceleration rate. This is 3 meter per second square. Then you have perception reaction time. Equals 1 second. Then you have entry delay. 1 second. Okay, so next is cycle length. That's 60 seconds. Then you have green time. So a lot of data given. 25 seconds. Saturation headway is also given. So that's 2 seconds per vehicle. And 11 is startup loss time. That's 2 seconds. Finally, I think you have clearance loss time. That's 1 second. So you have to solve a problem based on this entire data that you have. So maybe I'll write down the problem in the next one. The first one, okay, let me write it down here itself. The yellow change, find the yellow change interval in seconds. Okay, so what would be the approach to solve this problem? Let's see how we can solve it. Yeah, so there is a formula that you have learned in the class. So you can directly apply those and you can get the solution. So I'll maybe display it for a bit and so that you can get the data and then work it out and tell me the answer and then I'll solve and check if that is correct or not. So let me, the value of G, okay. Okay, so that is not given, is it? Okay, got it. Yeah, so it's given actually. G is grade, right? It's written here. Grade. Grade of the approach. So answer you are saying is 4, around 4, is it? Okay, so let's check that. Maybe I'll just solution. I'll give you in the next slide. So the formula is y equals, it's actually small y x e plus, so you have 0.28 v of 85, which is the 85 percentile, that's speed. This divided by 2a plus 19.6 g. So now, what is t? T is the perception reaction time. So that's given as 1 second. So this is 1. And then the 85th percentile speed, which you have to find, that's 60 kmph, and this has to be in kmph as well, so that's fine. So next you have this 2 times A is deceleration rate, which is given as 3, and then you have this 19.6 times, this is given, grade is given as 3%, so that should be uh, 0.03. So this is 3 divided by 100. So that should be your answer, and let me work it out and check if what is said is correct or not. So it's 2 times 3 plus 6. Okay, I'm getting a different answer, I think. Okay, so what is the answer? Someone wrote it as 4, is it correct? What do you, what do you say? Add 2.5, value of A is 2.5. Okay, I'm giving you a different problem altogether. Why do you just choose whatever value it's there on the slides or what? Here is it 2.5. Is there any question related to this? Okay. How do you know that it should be exactly 2.5? That's nice. You seem to know all the answers, but what I gave, you didn't solve that problem. So if you get something like this in the exam, you'll not be getting the correct answer. Here it's not 2.5, it's 3. So you have to be careful what numbers are given. Okay, so the answer is not obviously 4. You have written that's wrong. So the answer is, let's check, it's 3.55. Okay, so your answer is 3.55 seconds. Let's move on to the next, I think, problem. So the next one, I'll just write it here. What is the value of the red clearance interval in seconds? So let's answer this as well. So there is another formula for this one. So let me check this. It's again very simple. It's AR equals W plus L divided by 0.28 P of 83, sorry, 85 minus T of S. Okay, so what are W here? That's the width of the intersection stop line. So this is given as 30 meter. Then you have L, that is given as length of vehicle in meters, and that's 5. So that's 35. This is 30 plus 5 divided by 0.28 times V85. So V85 is 60 kilometers per hour. And then you have TS, which is the conflicting movement startup delay. So is that given here? Okay. So this value is, yeah. So this is 1 seconds. This is given as, yeah. So that should be 1. So this will be your answer in seconds. So that's 35 divided by 0.28 divided by 60 minus 1. So it's 1.08. So that's the correct answer. Okay, so yeah, no one replied, but anyway, it was a simple problem. Next one is the effective green time that I'll be asking. Okay, so here again, that should not be too difficult. So first you have to find, I think, TL, then you have to find YL, and then you have to find the small GL. So some of the values are given already. So can anyone solve this and tell me what the answer is? First, you have to find the total lost time. So your effective green time, basically, let me write down the formula. So this GL equals capital GL plus YL minus TLI TLI. Now you have to find these components individually. So let's do it in the next slide. So here you have first you can find out what your TLI is. That's the total lost time. So let's calculate that. So that's L1 plus L2, where this L1 is the lost time, and then you have the clearance lost time, which is L2. So startup lost time plus the clearance lost time. So your YL, sorry, not YL, this is TLI. This is small L1 plus L2. So let's see the data. Startup lost time is given as 2 seconds and clearance lost time is given as 1 second. So that's 3 seconds. So this is 3 seconds. Next is what you have to find is, so this part is done, TLI should be small t. Then you can find out what YL is. So to find YL, okay, so you have already found out two values, which is this small y, which is the yellow change interval in seconds, and the all red time, this AR, the red clearance interval in seconds. So you have to add those two up to get this YL. So this is Y plus AR. So your Y is 3.55 and AR is 1.08. This is 3.55 plus 1.08, which is 4.63 seconds. And finally, you have to find the GL value. So the capital GL value, I think it is already given in the problem, which is the green time. So the green time is 25 seconds. Okay, so now you have everything. So it's GL plus YL minus TI. It's 25 plus 4.63 minus 3. So that's 26.63 seconds. So that's the correct answer to this problem. Okay, so let's see if anyone got this. Yeah, 26.65. Yeah, around that only. Correct answer. Okay, so yeah, data you are asking. Yeah, data is maybe you can just quickly take a photo or so, because I'll be solving, I think, another one or two problems related to this. So just take a screenshot of this. Okay, if you're done taking the screenshot, then I'll move to the Next problem. Yeah, so let's discuss the fourth one. So this asks you about what is the capacity uh, in vehicles per hour for the approach. So for this one, you have to, I think you have to get the saturation headways first, and then you have to get the effective green as well as the cycle length. So that should give you the value of the capacity of that approach. So the formula is Ci equals Si times Gi divided by capital C. So here you have to find the individual components first. So what is your Si and so on. Gi is, I think, this should be small gi, sorry. In fact, this I wrote it as L, but this should be I ideally. So let me just quickly modify this. Yeah, now it's consistent. So GI you know already. C from the data it should come, and SI I think you have to calculate. So C is your cycle length that is given. So what is the value of SI to find? So this is the saturation headway related to that. So it's given as, so this one is the flow, sorry, here is the data. Saturation headway is given as 2 seconds per vehicle. Okay. Anyone got anything? 642 is the final answer that one of you was saying. You're saying SI equals 3600. Okay, let me check. So it's actually 3600 divided by H, which is the saturation headway, right? So saturation headway is given as 2 seconds per vehicle here. So this comes out to be, okay, I think you wrote, yeah, 3600 by H, so that's correct. So this is 1800. Then you have GI, which is 26.63 seconds. C is given as 60 seconds. So this unit should be vehicles per hour. And finally, that gives you CI, which is 1800 times 26.63 divided by 60. So that should be the answer. And let me calculate this quickly. 00 times 26.63 divided by 60. Okay, I'm getting a different answer, 798.9. Someone wrote some 635, was it? 642. Okay. Yeah, 642 was not correct. 799. Yeah, it's close to that. Yeah, that should be the correct answer. Okay, so I think, but I don't know why did you make that mistake. Let me check. Okay, so that's fine. Let's move on to the next problem. So the next one is somewhat similar, but it's okay. It has some new data, I think. Okay, so if the approach has an has a flow rate of 600 vehicles per hour, what is the uniform delay per vehicle expected under these conditions? The conditions are given above, right? The data that have been shared before. So for this one, what you have to do, so first I think you have to get the VYC ratio, and accordingly you have to find this uniform delay per vehicle. So the volume I think is given as 600 vehicles per hour. C is also I think calculated already. Yeah, so let me just quickly check what is the uniform delay formula. Okay, so I haven't gone into the discussion of this component, which is delay as performance measure, but anyway, let's solve this problem. So this is this uniform delay UD equals 0.5 times C, sorry, C is cycle length, then this minus, sorry, 1 minus G by G is small, G by C, so this whole square divided by 1 minus G by C times X. So that's the formula where C is the cycle length, G is the effective green time, C means this capital C is the cycle length, small c is the capacity of the intersection approach, so that we have to check, and X is the V by C ratio or the degree of saturation, whatever you call it. Okay, so let's find out these values. Capital C is the cycle length, which is given as 60 seconds. Then you have this small g, which is the effective green time, which you have calculated. I think this 26.63 seconds. Okay, so let me check if I'm getting it correct. Yeah. Then you have uh, this small c, which is your capacity. Okay, so I think something that's off. Yeah, just checking this convention of capital C and small c. So there is a doubt. Okay. Think, okay, small c is the capacity of intersection approach, and that is given as 798.9 vehicles per hour. And then you have to find x. Okay, I think okay, so I think here I have written it wrong. So this should be capital C and this should be capital C as well. Small c is the capacity of the approach. This is used in calculating x. So x is V by C ratio, and there you have 600 divided by 798.9. So yeah, slight mistake I made with this thing, but now it should be fine. So this gives you a value of 0.75, and now we have to just put this value. So UD is 0.5 times 60 times 1 minus G by C ratio is 0.44 divided by 1 minus 0.44 times 0.75. So that should be your answer in seconds. Okay, so let's calculate it. Yes, or it should be around 14.04 I'm getting. Okay, so did anybody get this? Yeah, I think it should be correct answer. EYC is 0.75. Yeah, correct. 13.95. I think you got it because of some approximation issues. So yeah, I think that should be the correct answer. Okay, so that's nice. Let's see what else we have that we can discuss in the last 15 minutes. See if there are some problems that we can solve. Okay, so okay, so maybe just briefly discuss. Yeah, yeah, this is the correct answer. Yeah, yeah. Okay, so let's discuss some of the questions related to this assignment. So there is one question which just says which of the following are characteristics of pre-timed signal controller. So if you go through this, I think lectures, you'll find this there are two different types: actuated signal and pre-timed signal controllers. So the first one is option A is variable green times. Next one is fixed cycle length. Next is fixed sequence of phases. And the fourth one is used at isolated intersections. Yeah. So what would be the answer to this? It's simple, right? So there can be multiple answers to this as well. Okay. Then what you got? VCT. Yeah, that's correct. So B, C, and D, both all of these are correct. There are no variable green times that happen in pre-time signal controllers. There is fixed green times and fixed sequence of phases, fixed cycle lengths, and typically used in isolated intersections. So let's okay, data true or false. So this says critical lane group represents that lane group in a phase which has the lowest flow rate. So what would be the answer to this? It's again directly getting from the slides. It's simple. Okay, maybe I'll just put some more into it. Clearance lost time includes component of only yellow interval. Next is startup lost time is associated with the first three or four headways as drivers react to the react to the green signal. Next you have total lost time. It's the difference between the startup lost time and the clearance lost time. Next is end gain is the sum of yellow change interval and red clearance interval. So let's see what would be the answers to this five true or false type questions. Okay, any answers to this? Okay, not yet. So lane groups and movement groups were discussed in the slides. So it should not be, I think, too difficult to answer these. So let's see if anyone could answer. Okay, so the first one would be false because it represents the highest flow rate. Next one is directly related to what figure. Maybe I'll just add and quickly discuss. Yes, sure. Sure. So let me add this figure. So this one is relevant to that question, the remaining ones, right? So here, let's see what second one says. Clearance loss time includes component of only yellow interval. So that is actually not true. Let's check. Yeah, so clearance loss time is this L2, and it says it includes component of only yellow interval. That is not true because it includes from all rate as well, and that's why it's false. Next one, it says startup loss time. Okay, anyone answer anything? Okay, not yet. Okay, next one is startup loss time is associated with the first 3 or 4 headways as drivers react to the green signal. So this is actually true because the effect is towards the like initial portion of this first 3 or 4 headways. So this is true. Next is total loss time is the difference between startup loss time and clearance loss time, which is not true because the total is this L1 plus L2, which is the startup loss time plus clearance loss time. So this should be false. Then end gain is the sum of yellow change interval and the red clearance interval. Okay, end gain is this one, yellow change and red clearance, which is obviously not true. So yeah, let me quickly check this. So this is also false. Okay, so think that's pretty much it. In the assignment, maybe just let me quickly open it. So I think these you will be able to answer. It should not be too difficult. It's directly from the class. This is also, I think it will be from that delay as a performance measure. From that module, you can answer this. This, I think we have discussed similar problems already. I think exactly those were not the same. I think I had 2, 3, and 9 and so on. Then you have this one. Uh, this is with respect to signal control operations. And again, it's a true false types question. This is, I think I didn't go into the much details, but again, this lane groups were thoroughly discussed during the sessions. Yeah, this is again similar and from signaling and so on, and you'll find it in the slides as well. Yeah, these problems I think you'll be able to answer. I think we didn't solve the exact problem this because that's given to you, so you should solve this, and it's similar to what we have discussed today. And these you can find in the slides. This is also a similar problem that we discussed today. Uh, the answer, yeah, will be different because this configurations and everything have been different. Yeah, this is also, I think, you can answer it. So it's again related to signaling and so on. And I think we discussed a similar problem in the class. So yeah, not exactly with the same values, but yeah, this B by C ratios and so on, the capacities and these things, effective green, I think we saw similar concepts there. Then, yeah, this is another simple problem, I think, directly from the definitions. This is also given in the slides with many, I think, are listed down as well. And this is again a true false type problem. I think you can answer this as well. So I think, yeah, this assignment, it's good that I have solved something different from what is here. So it's up to you now to solve this. And I think you'll be able to answer all these questions. It should not be a too difficult job. So yeah, I think, okay, is there any message? 14.1, please. Okay. Yeah, I won't be giving you the answer or discuss anything. But anyway, this one, okay, you're talking about. Yeah, so yellow change interval, red clearance interval, these are given. Cycle length, green time, total lost time. The approach flow rate is V and saturation flow rate is S. Then what is the V by C ratio? Yeah, so this you have to do it in terms of V and S. So these values are not given. So I think in my problem also, I had V by C ratio as the sub problem. So I think here, if you see this, uh, maybe I did it here. Yeah, this V by C ratio, the X that I found out here was having this. So this here V is given as V only, there is no value. The C you are finding out from this previous ones, and it depends on the saturation flow, which is also given as S here, no value is given. So you need effective green and the cycle length, those values are given. So yeah, green, effective green, I think you have to find out. Total, this green time and everything is given. And cycle length is given as well. So that should not be a problem, right? So once you have that, it's pretty simple. All the formulas are there in the slides, so I don't think it should be a problem. I think you'll work it out, right? Formula, okay. It's V by C, right? Ratio that you are asked. And uh, you already, V is V, so that's done. C is what you have to find out here. And for finding out C, the formula is already written in the slides. So I cannot give you everything. Like I won't give you the answer right away. It's up to you now to figure out what should be the answer to this. Yeah, I hope it should be clear. And if you still have a doubt for this, we can discuss it next week once the assignment solution is released and so on. Okay. Yeah, so it's almost time. So I think I'll stop the discussion. So I know I couldn't cover everything, but it's fine. Like I think you'll be able to figure it out on your own. And if you have any doubts, you can always post it in the discussion forum, or we can discuss it next week as well. So thank you. Yes, see you all next week. You can leave the meeting if you